Now we're ready to discuss the susceptibility of Pauli paramagnets, that is paramagnetism, due to free conduction electrons. Now, first of all, for a free electron, we don't have an orbital angular momentum contribution to a magnetic moment, so we can only consider the moment along the field direction to be given by the spin, and that will be equal to m is minus g Bohr magneton ms, which can be plus or minus a Bohr magneton for a free electron. So we have only a Bohr magneton contribution because no orbital motion for the free electron. It only has spin. If the magnetic moment is along the field direction is plus a Bohr magneton and the magnetic field is up, then this causes an energy of minus mu 0 mu bh. So the energy of the up spins will be lowered by this amount. So energy lowered by mu 0 mu bh. So for up moments, which means down spins. So that means we are talking about m is plus Bohr magneton. That means we are talking about a down spin, so that the moment is up. Now, when the magnetic moment is minus a Bohr magneton, that means we're talking about an up spin. The energy is plus mu 0 mu bh, so energy will be raised by plus mu 0 mu bh. So as you can see here, so if you plot density of states versus energy, it's proportional to e to the 1/2. If you put the energy in the y-axis and density of states in the x-axis, then you can see that energy is proportional to density of states squared, which means you have a parabolic relationship for E versus dE. And you can see that in this parabolic relationship at zero field, since the integral under the density of states versus energy curve gives us the total number of electrons by definition of density of states. Remember, density of states was dN dE. So we see that we should have the same number of up spins and down spins. Therefore, we will have zero moment at zero field. And when we have an applied field, the energy is lowered by mu 0 mu bh for down spins. And remember, down spins have a up moment. So there's going to be, so this is basically the spin direction. Spin up. This is spin down. That means moment up and moment down. So we have a lowering of the energy of down spins by mu 0 mu bh, and the lowering and the raising of the energy of up spins by mu 0 mu bh. So our task is to calculate the amount of imbalance between the number of up spins and down spins that we have created by applying this magnetic field. So we can calculate the total number of down spins. So let's calculate the total number of down spins. This is going to be the integral 1/2 integral from minus mu 0 mu bh to the Fermi level, E Fermi, density of states at energy E plus mu 0 mu b h dE. And why is that the case? So since the energy has been lowered by mu 0 mu b h, so the minimum energy is not 0, it's minus mu 0 mu b h. If you substitute for energy E minus mu 0 mu b h in density of states, you get density of states minus mu 0 mu b h plus mu 0 mu b h. That would give you density of states you originally had at 0. So the value you originally had at 0 is here, that is 0, and therefore you should recover the same result when you do this. So the shift of the y-axis in the negative direction has to be reflected as an increase in the energy argument in the density of states function. So it will be minus mu 0 mu b h to E Fermi, density of states E plus mu 0 mu b h times dE. Now, why is there a 1/2? So if you remember, in the density of states calculation, we have taken into account the fact that we have both an upspin and downspin allowed for a given quantum state. But here we're talking about only one type of spin, therefore we should divide this by 1 over 2, divide this by 2. This is basically only down spins. So we are considering only down spins. And the same thing applies for if you consider up spins, a similar argument applies. So if you want to calculate total number of up spins, how would we calculate this? This would be 1 over 2 integral from plus mu 0 mu b h to the Fermi level, density of states E minus mu 0 mu b h dE. Why? Because when I substitute E is equal to plus mu 0 mu b h, here I should get 0, and that's what I get. So this is correct. Okay, so we're trying to calculate the imbalance in the number of up spins and down spins. So if I call m total the net moment due to these conduction electrons, it will be equal to, because each spin gives me a Bohr magneton, and then I have the 1 over 2 factor here, integral, first I should consider the down spins, up moments, minus mu 0 mu b h to E Fermi, density of states E plus mu 0 mu b h dE. So that's the up moment, number of up moments, minus the integral from plus mu 0 mu b h to E Fermi, density of states E minus mu 0 mu b h dE. That is the number of down moments. So at the end of the calculation I will get the net up moments. So now let's have x equal to E plus mu 0 mu b h, so that dx is equal to dE, and when energy is equal to minus mu 0 mu b h, x is equal to 0. When energy is equal to E Fermi, x is equal to E Fermi plus mu 0 mu b h. And I will have a similar transformation for the other integral. Let's have y is equal to E minus mu 0 mu b h, so that dy is equal to dE. And when I have energy is equal to plus mu 0 mu b h, y is equal to 0. When I have energy is equal to E Fermi, y is equal to E Fermi minus mu 0 mu b h. So with this transformation, my total moment, total up moment, becomes mu b over 2, Bohr magneton over 2. The integral For minus mu 0 mu b h, I will substitute x equals 0, and for E Fermi, I will substitute E Fermi plus mu 0 mu b h, density of states x dx, and then I have minus at mu 0 mu b h I have 0, at E Fermi I have E Fermi minus mu 0 mu b h, density of states y dy. And you can see that if it's an x or y, it doesn't matter. It's the same thing that we are integrating. So you can write this as let x and y are energy E. So I can basically see that this is nothing but Bohr magneton over 2, the integral from 0 to E Fermi plus mu 0 mu b h density of states dE, and then I have plus the integral from E Fermi minus mu 0 mu b h to 0 density of states energy dE. So you can see that I have switched the order of the limits, so I get the minus sign becoming a plus. So one integral is from 0 to E Fermi plus mu 0 mu b h, the other one is from E Fermi minus mu 0 mu b h to 0. Basically, this is telling me that the total moment is mu b over 2, the integral from E Fermi minus mu 0 mu b h to E Fermi plus mu 0 mu b h density of states dE. So this is going to give me the answer that I'm looking for. Okay, so let's move on. Now, if you remember the density of states as a function of energy, basically the integral I'm supposed to perform is around the neighborhood of the Fermi level. So if I replot my density of states as a function of energy here, you can see what I'm doing. Here is the e to the 1/2 dependence. This is the Fermi level. Now I'm supposed to find the area for E Fermi minus mu 0 mu b h, and then for E Fermi plus mu 0 mu b h. Okay, so the area I'm looking for is this area. I'm going to approximate this area because mu 0 mu b h is a very small number. Typically mu 0 is small, mu b is small, so typically this is a very small interval. So I can approximate this area to be 2 mu 0 mu b h times the density of states at the Fermi level. So basically I consider this area to be equal to the red area is equal to the blue area. So that's my approximation. So with that, the total magnetic moment will be mu b over 2. The area is 2 mu 0 mu b h times the density of states at the Fermi level, and the 2's will cancel. So I will obtain Bohr magneton square mu 0 Bohr magneton square h density of states at the Fermi level. And density of states at the Fermi level I found previously to be 3 over 2 the number, total number n, total number of electrons divided by the Fermi energy. So I find that the total moment, the net up moment will be mu 0 mu b square h 3 over 2 E Fermi times the total number of electrons Ne. And in order to get magnetization, I have to divide this by volume, and so the magnetization will be 3 over 2 the number density for electrons, NeV, mu 0 mu b squared divided by E Fermi multiplied by H. So the susceptibility, Pauli susceptibility, I find m over h to be 3 over 2 the number density for electrons, mu 0 mu b squared divided by E Fermi. So indeed this is not temperature dependent. Okay, so the Pauli susceptibility that I find is temperature independent, and one thing I haven't taken into account is that the electron trajectory is unaffected by the magnetic field. That's my assumption. The electron trajectory motion, even if it's a free electron, is affected by the magnetic field also. It's like an orbital effect. And Landau has shown that for free electrons, due to the trajectory of the electrons in a magnetic field, the precession around the magnetic field causes a diamagnetic susceptibility, which is roughly 1/3 of the paramagnetic susceptibility. So the true susceptibility, chi, is the Pauli susceptibility minus Landau susceptibility. And so we find that this is Pauli minus 1/3 Pauli, which is 2/3 of Pauli susceptibility, and that ends up getting rid of this 3 over 2 up front. So we obtain mu 0 Bohr magneton square number density of electrons divided by the Fermi energy as our true susceptibility of Pauli paramagnets. So one effect that we haven't considered, that is the effect of the magnetic field on the trajectory of the electron, does cause a correction, a diamagnetic correction to the susceptibility. There are other secondary effects that we haven't considered. Secondary effects, for example, there is also the core shell electron diamagnetism, which is present in all materials. We haven't considered any band effects, so electrons that are contributing to bonding that are in bands, what will be the effect of band formation on those electrons. Actually, the valence electrons are free, but basically these electrons that are residing in the bands will be in the lower energy levels. And also we haven't considered any electron-electron interactions. Therefore, we said that these electrons are free to move. And also we didn't consider any electron lattice because we have ions residing in the lattice, electron lattice, free electron lattice interactions. Okay, so these will all come into play in an actual experiment where we will see corrections. Okay, examples of Pauli paramagnets. Aluminum has atomic number 13. Its configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So this has 3 valence electrons that are released into the lattice. So it's a Pauli paramagnet. Copper is Z is equal to 29, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. So it has 1 valence electron that is released into the lattice. So these are Pauli paramagnets. Okay, so in summary, we talked about susceptibility for Pauli paramagnets. We know density of states as a function of energy. And if you look at the area under density of states as a function of energy curve, that gives you the number of electrons. So when we apply a magnetic field, there will be energy splitting for spin up and spin down electrons such that up moments that are pointing in the direction of the applied field will have a lowered energy. So down spins will have a lowered energy, and up spins or down moments will have a higher energy. So we need to calculate the imbalance in the number of up spins and down spins in these states. So what we will find out is that the integral from minus mu 0 mu bh to E Fermi of density of states multiplied by 1/2, because we're considering only one type of spin, will give me the number of down spins. So basically what is happening here is that these extra up spins are flipping, and they're going to be filling this area, and then we can find the number of down spins, how many extra number of down spins we have obtained at equilibrium. So this region is basically flipping, and the net number of up spins is, because for each spin I have a Bohr magneton contribution, there is no orbital angular momentum to consider. Mu b over 2, the integral from minus mu 0 mu bh to E Fermi, that will be accounting for down spins, and minus the integral from plus mu 0 mu bh to E Fermi, that will be accounting for the up spins. So by performing this integral, I have found that really what I'm trying to do is to calculate the area in the vicinity of the Fermi level in the range E Fermi minus and to E Fermi plus mu 0 mu bh. So that area can be approximated as the area of this rectangle 2 mu 0 mu bh. So that is this length, multiplied by density of states at the Fermi level, that is this length here. So this will give me the area of the rectangle, which is approximately the same thing as the area in this region. And why does this approximation work? Because mu 0 mu bh is much smaller than Fermi energy. That's the approximation. So we find that the resulting Pauli susceptibility is 3/3 number density of electrons. So NEB is number of electrons divided by volume V. V is volume. However, this 3/3 factor disappears when you consider the diamagnetic contribution from the precession of the electrons, net precession of the electrons around the magnetic field that was suggested by Landau. So we find that instead of having this 3/2, we have mu 0 mu b square number density divided by Fermi level as susceptibility, which is temperature independent. There are other effects we didn't consider. Core shell electron diamagnetism, which is present in all materials. There are band effects. There are electron-electron interactions. There are electron-lattice interactions for these free electrons. So basically, by ignoring these interactions, we have said the electrons are free to move. And I have given two examples, aluminum and copper, where we see Pauli paramagnetism. So Pauli paramagnets are, remember, paramagnetic metals.